Solving systems of equations graphically. So if you're wondering what a system of equations is, that would be the grouping of two or more equations. We're going to specifically look at systems of linear equations. So if I gave you this system, what is the solution? Okay, well, let's first talk about what comes to mind when you hear or see the word solution. Maybe you think about solving equations such as 3x equals 12, and it doesn't take long for you to come up with the solution 4. Maybe you solved by dividing both sides by 3 to get x equals 4. Maybe you just recognize that 3 can only be multiplied by 4 to equal 12. So what is a solution? A solution makes an equation true. So the system I gave you just a second ago, when graphed, it looks just like this. Okay? So what if I asked you for the solution for this system now? When we're given a system of linear equations, we can graph both equations, and the intersection point is that point that the two lines have in common. And so here, the point 6, 1, right here, that intersection point, that ordered pair lies on both of our lines, right? Which means that point makes both of our equations true. Therefore, that ordered pair is the solution to our system. So for those of you taking notes, systems of equations can be solved using a graph. The solution is the place where the two lines intersect. If an intersection point exists, in order to solve a system graphically, you must make sure that both equations are in slope-intercept form. You can graph them by first plotting the y-intercept and then using the slope to find the next point. So let's practice. All right, y equals 1/2 x minus 2. So remember, when graphing a linear equation, it needs to be in that slope-intercept form. That means we have to have y equals. All right, so our y-intercept is -2, so we're going to plot -2 on the y-axis. And then our slope is 1/2. And remember, slope is the change of y values, right? That's up or down, that's our rise, divided by the change of x values. That's left or right, that's our run. So we're going to go up 1, right 2. We continue that rate of change. Okay, remember, if we can go up 1, right 2, we can continue the line in the opposite direction by going down 1, left 2. Okay, and so we have to connect the points in a line and then draw those arrows to represent that this line is continuous. Okay, now y equals -3x plus 5. That has a y-intercept of 5. And our slope is -3. And remember, that's the same thing as -3 over 1. So we're going to go down 3, right 1. Down 3, right 1. Okay, and we could also have gone up 3, left 1. Now, before we even think about the solution, let's check. Here we had a positive slope, so that should be increasing, and it is. Here we have that negative slope, so it should be decreasing, and it is. Okay, so now what is the solution? Well, where do our lines intersect? They intersect right here. Remember, ordered pairs, that format x, y. Here our x coordinate we see is 2. And then the y coordinate we see is -1. So our solution here is 2, -1. And we could check that, okay? You're wondering, how could we check that? Well, if it's a solution to the system, it needs to make both equations true, okay? So for that first equation, we substitute in -1 for y. We substitute in 2 for x, okay? -1 equals -1, that is true. And then we could have substituted that into the second equation as well. And that also gives us -1 equals -1. So since the ordered pair 2, 1 made both equations true, it is our solution. Okay, let's look at our next example. All right, y equals -1/3 x plus 1. Plot our y-intercept at 1. Our slope takes us down 1, right 3. We can go the opposite direction as well. And that should be a decreasing line because it's a decreasing slope. All right, second equation. Y-intercept of -3, and our slope's going down 1, right 3. Okay, so what is the solution for this system? Okay, so a solution is an intersection point, right? Do these two lines intersect? Okay, they don't. Well, what if we extend the lines, right? Because we know this continues forever. Will they ever intersect? Well, these lines have the same slope and different y-intercepts. These are parallel lines, meaning they have no intersection point. They never touch. They never intersect. So we actually don't have a solution. We have no solution. Parallel lines result in no solution. Okay, let's look at our last example. Okay, so that first one, can we graph that right now? No, we need it to be in slope-intercept form. Okay, to get it in slope-intercept form, we need to solve for y. So we're going to subtract 2x from both sides. 2x minus 2x gives us 0. And 8 minus 2x is just 8 minus 2x. Or you could reorder that as -2x plus 8, your call. And then we divide both sides by -4, which means here we want to divide every single term by -4. So that gives us y equals -2 plus 1/2 x. Well, that's weird. Look at these two equations. If we were to reorder this one, we have the exact same equation. Okay, so that means if we were to graph this, what are our two lines going to do? If you're thinking they're going to be right on top of one another, you are exactly right. Here, our two equations in our system give us the exact same line. So what's the solution? Now, the solution here is not all real numbers, because is this right here a solution to the system? No, it's not on our line, right? Only all of these points are solutions, okay? So that means we have infinitely many solutions, okay? Every ordered pair that makes this equation true is a solution. And since there are infinitely many points on a line, we have infinitely many solutions. So in conclusion, a system of linear equations can have one solution, infinitely many solutions, or no solution. Okay? When it's one solution, that means it has different slopes, right? Infinitely many solutions means it has the same slope, same y-intercept. No solution means same slope, different y-intercept. Okay? And how do you solve systems graphically? Put them into slope-intercept form and graph and look for the intersection point.